Good morning, everyone. I'm Sherry Ann Sakriyas, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. Today, I'll be discussing on MEMS and microactuators. This is a topic that comes under the course EC465 MEMS for S7 EC students. The topics of this presentation are as follows. We will start with an introduction to what is a microactuator, and then we will look at the various principles of actuation, like actuation using thermal forces, using shape memory alloys, using piezoelectric crystals, using electrostatic principles. Then we will discuss on the working principle of the commonly used actuators such as micro grippers, micro motors, micro valves, micro pumps, and micro accelerometers. The reference textbooks are Foundation of MEMS by Chang Liu and MEMS and Microsystem Design and Manufacture by Tyran. Now, a microactuator is one of the core elements of a microelectromechanical system. A microactuator is a device that is used to control or produce some kind of mechanical motion. So this figure shows the block schematic of a microactuator. So it contains a transduction unit, and the input to the transduction unit might be the output of some processor or controller, and this transduction unit is responsible for converting the signal from one form of energy to another. And then you have a micro actuating element that is responsible for producing some mechanical motion such as force or torque. Now the driving power for actuators, it varies depending upon the application. For example, the deflection of a bimetallic strip can be used to control the on-off switch in an electric circuit. Or if you consider most of the electrical actuators such as your motors, solenoid devices, they are driven by electromagnetic induction and so on. Now the working principle of actuators, there are basically four main principles on which actuators work. So the actuators can work on the basis of thermal forces, shape memory alloys, piezoelectric crystals, or electrostatic principles. Actuation using thermal forces. Now, most of the solid materials, when subjected to a temperature change, has a tendency to deform. So, for example, if you consider a solid rod having a length of L, and if it is exposed to a temperature change of delta T, then the length of the rod will extend by delta L, where delta L is given by delta L equals alpha times delta T, where alpha is the coefficient of thermal expansion. Now, bimetallic strips are actuators which work on the basis of thermal forces. Now, what is a bimetallic strip? A bimetallic strip is made by bonding two materials having different values of coefficient of thermal expansion. This figure shows a bimetallic strip that is being made by bonding two materials having a distinct value of thermal expansion coefficient. So here the upper layer has a thermal expansion coefficient alpha 1 and the lower layer has a thermal expansion coefficient of alpha 2, and here alpha 1 is greater than alpha 2. So when this bimetallic strip is heated by external sources, what will happen is the two materials will expand differently. Because of that, this bimetallic strip is going to bend. Okay, but once the applied thermal force is removed, it will return to its initial reference shape. Okay, so basically when it is subjected to a change in temperature, the material is going to change its geometry. So this is an actuation principle that is used in micro switches and relays. The next kind of actuation is based on shape memory alloys or SMA. So shape memory alloy is a material that remembers its geometry at a high temperature of production. So for example, consider an alloy. It has a particular shape at a temperature of capital T. Okay, so this alloy will deform into another geometry or shape at room temperature. Okay, these deformed structures, however, when it is heated back to the elevated temperature of capital T, it will return to its original shape. Okay, so such a material is called a shape memory alloy because it remembers its original geometry or shape. Examples of shape memory alloys are titanium nickel alloys, nitinolar, etc. So this figure shows how microactuation can be achieved using a shape memory alloy. Okay, so you can see that in this figure there is a silicon cantilever beam to which you are attaching a strip of shape memory alloy such as titanium nickel, and this is connected to a resistance heating strip. Okay, so now assume that this shape memory alloy has a bent shape at a temperature of T. Okay, and at room temperature the beam is straight. Okay, so when you heat this silicon cantilever beam with the SMA strip to the temperature T, the shape memory alloy will remember its original bend shape and it will deform. So the deformation of the SMA strip will cause this attached silicon beam also to deform, and thus microactuation of the beam is achieved. So that is what is given over here. You have an SMA strip with a bend shape at a preset temperature of T, and at room temperature the beam is set straight. So when the beam is heated back to the temperature T, the SMA strip is again going to bend. The deformation of the strip is also going to cause the silicon beam to deform, thus microactuation is achieved. So this type of actuation can be used in micro rotary actuators, micro joints, robots, micro springs, etc. Now actuation using piezoelectric crystals can be explained as follows. Certain materials such as quartz will deform on applying an electric voltage. The reverse effect is also possible. That is, on applying a mechanical force to deform the structure, an electric voltage can be generated. So this phenomenon is known as piezoelectric effect. So here the first figure over here shows a piezoelectric crystal to which you are applying mechanical forces to deform the crystal structure, and an electric voltage gets generated. In the second figure, the reverse effect is seen. That is, when you apply a voltage across a piezoelectric crystal, it results in a mechanical deformation. So this figure shows how microactuation can be achieved using a piezoelectric crystal. Okay, so here you have a silicon cantilever beam which is attached to a piezoelectric material, and this piezoelectric material is being sandwiched between two electrodes, and a voltage is being applied across the piezoelectric crystal. Okay, so when a voltage is being applied, it leads to the deformation of the crystal, and as the crystal deforms, it leads to a bending of the attached silicon cantilever beam. Okay, so thus actuation is being achieved. So this kind of actuation mechanism is used in micro positioning or micro clamp circuits. The next type of actuation is based on electrostatic forces. So we know that the electrostatic force between two charged particles as given by the Coulomb's law is that there is a force of attraction or repulsion between two charged particles there's always proportional to the product of the charges and inversely proportional to the square of the distance between the two charged particles. Okay, so the attractive or repulsive force is given by F is equal to 1 by 4 pi epsilon Q into Q dash divided by R square, where R is the distance between the two charged particles and Q and Q dash are the charges. So this force can be attractive or repulsive depending upon whether the charges are like or unlike. Okay, so if the two charges are both positive or both negative, then it will be a repulsive force, whereas if the charges are positive and negative, then it will be an attractive force. So here epsilon represents the permittivity of the medium, and in the case of vacuum, epsilon naught is equal to 8.85 into 10 raised to minus 12 farad per meter. Now, if two charged plates are separated by a dielectric material with a gap d, then these plates will become electrically charged when a voltage is being applied across the plates, and this action will induce a capacitance in the charged plates that is given by C is equal to epsilon r epsilon naught A by d, where A represents the area of the plates, d is the distance between the plates, and epsilon r represents the relative permittivity. Now, if the length of each plate is L and the width is W, this can also be written as epsilon r epsilon naught into WL divided by D. So here the thing is that the electric charge will be maintained between the top and the bottom plates as long as a voltage is being applied to the system. Now, the charge which is stored in either of the plates, it can be instantly discharged if the plates are short circuited using a conductor. Okay, so thus there is an electric potential that exists, and the energy associated with this electric potential is expressed as U is equal to 1 by 2 into CV square, where C is the capacitance and V is the voltage applied across the plates. And so the associated electrostatic force that is normal to the plates, that is in the D direction, is given by Fd is equal to magnitude of dou U by dou X. So that is equal to 1 by 2 times dou C by dou X into V square. So we get an expression for the electrostatic force associated with parallel plates is given by Fd is equal to minus 1 by 2 epsilon naught epsilon r WL divided by D square into V square. Now we will look at a few microactuators which are commonly used based on the working principles explained so far. The first kind of a microactuator that we will be discussing is the micro gripper. So in a micro gripper, the driving force is the electrostatic force which are generated in parallelly charged plates. So this is the driving force that is used for gripping objects. So the kind of gripping force can be of two types. You can have a normal force or an in-plane force from a pair of misaligned plates. Okay, so the figure over here shows two different arrangements. In the first arrangement, you're using a normal gripping force. Okay, so here the disadvantage is that the electrodes consume a lot of space. So we go for the second arrangement. Here you have multiple pairs of misaligned plates. Okay, so this arrangement is preferred, and this kind of arrangement is also known as a Coulomb drive actuator. Okay, now this figure over here shows a micro gripper that is being implemented using Coulomb drive actuators. So here the gripping action, in order to initiate the gripping action, you're going to apply a voltage across the plates which are attached to the drive arm and the closure arm. Okay, so when you apply a voltage, what will happen is you have electrostatic forces getting generated that causes the drive arm to bend. Okay, so since the drive arm is connected to the extension arm, the arms for extension are going to close. Thus it helps in achieving the gripping action. So this kind of micro grippers are used in robots, micro manufacturing, microsurgery, and so on. The next type of actuator is the micromotor. So in a micromotor, the actuation force is based on electrostatic force. So here the basic principle is the sliding force which is generated by a pair of energized misaligned plates. So there are basically two types of micromotors, linear motors and rotary motors. So the first one is linear stepping motors. So in a linear stepping motor, it consists of two sets of base plates, okay, and each base plate consists of a number of electrodes, and the base plates are separated by a dielectric material such as a quartz film. Now each of these electrodes have a fixed length of W, and one base plate is fixed and the other is movable. So here the bottom base plate is fixed and it has an electrode pitch of W, and the top base plate is movable and it has an electrode pitch of W plus W by 3. So this figure shows the working principle of the linear motion between two sets of parallel base plates. So you can see that the bottom base plate is fixed and the top base plate is movable, and the bottom base plate, it has a pitch of W, whereas the top base plate has a pitch of W plus W by 3, and each electrode has a length of W. Okay, so initially the two set of base plates are misaligned by W by 3. Okay, so in the first step what happens is that the electrode pair A and A dash are energized. Okay, so on energizing the pair of electrodes A and A dash, it causes the motion of the top plate towards the left until A and A dash becomes fully aligned. Once the plates A and A dash become fully aligned, what will happen at that moment? The electrodes B and B dash will be misaligned by W by 3. Okay, so in the next step, the electrode pair B and B dash are energized. Okay, that causes the movement of the top base plate to the left such that B and B dash becomes aligned. Okay, so when B and B dash becomes aligned, now C and C dash will be misaligned by W by 3. Okay, so you have to subsequently energize the plates C and C dash. Okay, so this is done in a continuous manner in order to obtain the linear step movement of the top base plate. So the next type of motor is the rotary stepping motor. So the rotary motors are also driven by electrostatic forces and they can be constructed in a similar manner. So this figure shows the top view of an electrostatically driven micromotor. So you can see that from this figure you have, these are the rotor and these are the stator, and the electrodes are installed on the outer surface of the rotor and the inner surface of the stator. Okay, so just like in the case of your linear motors, the pitches of the electrodes in the rotor and the stator poles are mismatched in such a way that an electrostatic force is being generated due to the misalignment of the energized pair of electrodes. Okay, and here the ratio of the poles in the stator to the poles in the rotor is 3:2, and one of the main problems encountered during the design and manufacture of this micro rotary motors is the wear and lubrication of the bearings. Okay, so typically these motors, they will rotate at speeds of 10,000 revolutions per minute. So the next type of actuator is the microvalve. The microvalve is an actuator which works on the principle of thermal forces. So the function of a microvalve is to control the rate of flow. That is, the valve can be open or it can be in a fully closed state. So based on the state of the valve, you can control the rate of flow. The applications of micro valve is that it can be used in the manufacturing industry. Like for example, it can be used to precisely control the flow of gas in a manufacturing process, or it can be also used in biomedical applications when you want to control the flow of blood in an artery. Another application is that it can be used in the pharmaceutical industry, where valves are used as a principal component in microfluidic systems. So whenever you want to do a precise analysis, or if you want to separate certain constituents, we can use microvalves. This figure shows the schematic diagram of a microvalve. So you can see there is a silicon base to which a flexible silicon diaphragm is attached, and this over here shows the passage flow of the fluid. Okay, and here to this diaphragm a pair of electric resistance heating rings are attached. So on heating these electric resistance rings, what will happen is that the top diaphragm will move downward. Okay, so this downward movement of the diaphragm is going to close this valve, preventing the flow of the fluid. Okay, similarly, when you remove the heat from the diaphragm is going to move upwards. Okay, and as the diaphragm moves upwards, the valve opens, allowing the fluid to flow. Okay, so here the dimensions of the diaphragm that is shown in this figure, it is about 2.5 millimeters is the diameter and 10 micrometers thick, and this particular valve, it has a capacity of 300 centimeter cube per minute at a fluid pressure of 100 psi. Okay, so on the basis of thermal forces, you can control the opening and closing of this valve. The micro pump is another actuator. Here the actuation principle is based on electrostatic forces. So this figure shows a schematic diagram of a micro pump. So you have a deformable silicon diaphragm which acts as one electrode of a capacitor, and there is another top electrode, and across these two electrodes an externally applied voltage is being applied. And when a voltage is being applied, what happens is that the diaphragm tends to move upwards towards the top electrode. Okay, so as the diaphragm moves upwards, it leads to an increase in the volume of the pumping chamber. Okay, so that increase in the volume of the pumping chamber will reduce the pressure inside the chamber. This reduction of pressure will cause the inlet check valve to open. Okay, thus allowing the fluid to enter into the pumping chamber. Now when you remove this externally applied voltage, what happens is that the diaphragm will return to its initial position. Okay, so when the diaphragm returns to its initial position, there is a decrease in the volume of the pumping chamber. That means there is an increase in the pressure of the entrapped fluid inside the pumping chamber. So when the pressure crosses a particular threshold value, this outlet check valve opens, causing the fluid to be released. Okay, thus a pumping action is achieved. So in this particular pump, the dimensions of the pump are 4 cross 4 millimeter cross 25 micrometers thick, and the gap between this diaphragm and electrode is very small, approximately 4 micrometers, and using this kind of a pump, a pumping rate of 70 microliters per minute can be achieved at a frequency of 25 Hertz. So this shows here you can see the working principle explained. You have a deformable silicon diaphragm which acts as an electrode of a capacitor. By applying a voltage across the electrodes, the diaphragm actuates and moves towards the top electrode. This movement of the diaphragm will increase the volume of the chamber. This will reduce the pressure inside the chamber and thereby opening the inlet check valve, causing the fluid to flow inside. When the applied voltage is cut off, the diaphragm returns to the original position, so the volume of the chamber reduces. It increases the pressure of the fluid inside, causing the outlet check valve to open and the fluid is released. That is how pumping is achieved. So the next type of actuator is the microaccelerometer. The accelerometer is a device that is used to measure the amount of acceleration or deceleration of a moving object. So these accelerometers are widely used in the automotive industry. So it can be used, for example, acceleration sensors are used in the car suspension system and the anti-lock braking system. So they are in the range of plus or minus 2G range, whereas the acceleration sensors which are used to actuate the airbag in case of a collision is in the range of plus or minus 50G. Here G stands for your gravitational acceleration, which is 9.81 meters per second square. So this kind of accelerometers are also known as inertia sensors, which have certain actuation elements. So the principal components of an accelerometer are shown in this figure. So there is a proof mass which is supported by a spring, and this is attached to a dashpot in order to provide the necessary damping effect. And this entire structure is enclosed within a casing and then attached to the vibrating solid body. Now, since the proof mass is being attached to the moving object, you can measure and record the instantaneous displacement of the mass y of t with respect to time. So once you get the displacement y of t, the velocity associated with it is found by taking the derivative of the displacement with respect to time. So v of t is equal to dy of t by dt. So from the velocity you can find the acceleration by taking the derivative of the velocity with respect to time. That is, acceleration alpha of t is the second derivative of the displacement with respect to time. So alpha of t is d square y of t by dt square. And in order to find the dynamic force induced by the moving solid, you have to apply Newton's second law, which states that the force is directly proportional to the acceleration. So you have F is equal to m into alpha of t, where m is the mass of the moving solid. So F is equal to m into d square y of t by dt square. Now, in a microaccelerometer, however, there is no space for this coil spring, the dashpot, and even the proof mass. So generally, there are two types of microaccelerometers that are commonly used. One is the cantilever beam microaccelerometer, and the second one is the balanced force microaccelerometer. So this figure shows the structure of a cantilever beam microaccelerometer. So why we go for this kind of arrangement is because of the space limitation in a micro device. Okay, so here, as you can see in this structure, there is a silicon cantilever beam which is attached to a proof mass, and this forms the spring mass system, and there is an air in the surrounding space, and this is used to provide the necessary damping effect. Okay, and on top of this silicon cantilever beam there is a piezo resistor which is implanted, and that is used to measure the deformation of the attached mass. So by measuring that deformation, you can calculate what is the acceleration of the vibrating body to which this accelerometer is attached. Okay. So this is the second arrangement known as the balanced force microaccelerometer. So this kind of accelerometer is used in the airbag deployment system of automobiles. So you can see that in this arrangement there is a thin beam, and this thin beam is being attached to two tethers. Okay, and these tethers are made of elastic material and they are firmly fixed at one end. So this thin beam it acts as the proof mass. Okay, and to this beam you have an electrode plate attached, and this electrode plate is kept between a pair of fixed electrodes. Okay, so this shows the arrangement when the sensor is at rest, and this shows what happens when an acceleration is applied. So when an acceleration is applied, the proof mass will get displaced in the direction opposite to acceleration. Okay, so that movement of the proof mass can be recorded by measuring what is the change in capacitance between the pair of electrodes. Okay, so that is how you can measure the acceleration of the vibrating body to which you are attaching this microaccelerometer. Okay, so to conclude with, in this presentation we had discussed on what a microactuator is. We looked into the working principles of microactuators based on thermal forces, piezoelectric crystals, based on shape memory alloys and electrostatic forces, and then we discussed on the commonly used microactuators such as the micro pump, micro valve, micro gripper, and the microaccelerometer. Thank you.